Folks, welcome to lesson 23. All right, so if you take a look at the screen, you'll see the last question we solved in the previous lesson. And I think I had referenced the fact that, the idea of upgrading things like substitution and elimination to more than two equations with two variables, okay, is clearly something we can do. So here we've got three equations and three unknowns. But you have to imagine that there's nothing that would stop you from just continuing on, considering four equations and four unknowns, five equations and five unknowns, okay? Now, in particular, we actually solved problems involving more unknowns. So if you think back to these types of questions where you were being asked to determine some polynomial and you didn't know what the coefficients were. So let's make this ax cubed plus bx squared plus cx plus d. And you had to determine these four unknowns. You were solving a system with four unknowns. Now, why was this significantly easier to solve? How could it be that solving for more unknowns was relatively easy? So think back to what type of information you would have had when you were solving these types of equations. Well, folks, you're going to be writing a final exam soon. Good idea to remember this. So what type of information would I have given you here? Yeah, but if I was, sorry, not this wasn't, it's just supposed to be some function. So I'm not solving an equation. I'm solving for the unknown values in this polynomial function, okay? Okay, so you'd use the fact that it was differentiable, and often they might give you the derivative at a certain point, or tell you where the second derivative is 0. And what happens when you take the derivative of this function? That makes solving a problem with it, there you go, the d disappears. What about when you take the second derivative? The c also disappears. So you ended up with four equations that you were solving, but you were solving equations where some of these terms just disappeared altogether. Okay, so that's why we were able to get away with solving those problems without having to come up with some big new way of determining the solution, because we ended up with simple equations. So, you take the derivative, the d disappears. Take the second derivative, the c disappears. Very often they would give you the y-intercept of the function. So you would know the d value right away. So then you'd be left with only three unknowns to solve. So you were still solving a system of equations in that scenario. It just happened to be a relatively easier one, okay? But now you have to imagine that if you're solving something where all of these coefficients are non-zero, that it could start to get very complicated when you try to do this with even more equations. So at some point, as often happens in mathematics, is somebody had a bright idea. And they realized that as they were solving these problems, think about what you do. So what are the things we do to these equations to solve them? So tell me what algebraic processes were following. Even take at this first thing that I do. What types of operations am I performing? Okay, so let's start with multiplication. I'm multiplying both sides of an equation by some number, okay? As long as I multiply both sides of the equation by the same number, it's a legal operation. Okay, so if I multiply equation 1 by 2, this becomes 2x, this becomes minus 6y, this becomes minus 4z, this becomes negative 18. And when you think about it, what's the only thing that's changing when I multiply both sides of this equation by 2? or I multiply both sides of this equation by 3. What is it that's actually changing? Yeah, you realize that the x, y, and z, these letters that represent the unknowns, don't change. The only thing that changes are the coefficients to these variables and this constant term. Okay, now let's go with um, the other idea, the idea of elimination. You can add and subtract both sides of the equations. So here with equations 1 and 2, so I performed one legal operation by multiplying both sides of the equation by 2, and then I added the two left sides, and I added the two right sides, or subtracted the two left sides, subtracted the two right sides to form a new equation. Okay? Does it change the value of y and z when I perform this operation? No. But again, what is it that I actually manipulated when I add or subtract two equations together? What is it that changes? What is it that doesn't change? I'll give you a hint. It's not this, it's not a different answer from what was said before. There you go. You realize that the only thing that actually gets manipulated are the coefficients. So in the end, the x, y, and z, they never change. They just always stay the same. So somebody had the bright idea of saying, well, you know what? Since I'm only ever working with the coefficients, why bother writing out this whole equation? Why don't we just work with the coefficients? Okay? And this brought about this idea of working with these arrays, or what we call matrices, is that you rewrite this system of equations so that you're only writing out the coefficients of the x, y, and z, and then the constant term on the other side of the equation. Okay, and you come up with a system for solving these by working with this matrix, and we'll see what that looks like. Okay, in the end though, we're still solving a system of equations. So that means we're still using the same operations. Okay, we're still multiplying both sides of an equation by a constant. We're still adding and subtracting equations to create new equations that we can then work with. Okay, so we're going to look at what are called the elementary operations. And those are two of the elementary operations, is that I can multiply both sides of an equation by a constant, and I can add and subtract equations to form new ones with the same solutions. So whatever the solution for y and z in these two equations will be the same solution that you would get for y and z working with all three of them together. All right? There is one more elementary operation, and it's one that is not going to seem too useful given what we did to solve these problems earlier, but I think is going to become a little useful to us when we consider this alternate method. Okay, and in a sense it comes from this. Did it matter whether I started with equations 1 and 2? Did I have to start with equations 1 and 2? No. Okay, in fact, if you look back to the first one that we solved, I'm pretty sure, oh yeah, we did work with 1 and 2. So maybe it was a previous one where we didn't work with the first two equations. All right. I could have started with 2 and 3, and I could have worked with 1 and 3. I didn't even have to work with 1 and 2 at all. So the order with which I work with these equations is unimportant. So that third elementary operation is that I can switch around these equations at will. I could call this equation 1, this equation 2, and this equation 3 if I like. It doesn't make a difference. Okay? It's not something we really think about while we're solving these problems, but it is what we call an elementary operation. And essentially what it tells you is it doesn't matter which equations you start with. All right. So let's try to figure out how we're going to take Okay, and you see I've got the exact same question. It's going to be the first one we do, just so we can check our answer. So what I want to do is I want to take this system of equations and write it in such a way that I don't have to bother with writing out the variables. In fact, I'm not even going to bother with the equal signs here. Okay, I want to focus solely on the coefficients. And so what we do is we create an array where a row in that array is going to represent the coefficients of x, y, and z. And then the last element in the row is going to represent what the expression is equal to. Okay? But in order to make this work out, not surprisingly, we have to keep everything consistent. So the first column is going to have to represent the coefficients of x. The second column is going to be the coefficients of y. The third column, the coefficients of z. And the fourth column has to be what the whole expression is equal to. Okay, because remember, we're not going to have the actual equation to look at. So we need to make sure that we're very consistent in how we write this. So let's write it out. So remember, the first row is going to represent the first equation. Okay, but I'm not going to be writing out the x, y, and z. I'm just going to be using the coefficients. So 1, -3, -2, and then I've got my -9. Okay, my second row is going to represent the second equation, 2, -5, 1, and then 3. And then the third row is going to represent my third equation, -3, 6, 2, and 8. Okay, let's make this left side a little better. Didn't make that quite long enough. Okay, and what we do to make sure we're very clear that these represent the coefficients to my variables and these represent what that linear combination is equal to, we put a little dotted line to separate it out. Okay, and this is called a 3x4 matrix. Okay, so the fact that I'm putting the 3 first means the first number represents the number of rows, and then the second number represents the number of columns. Okay, and so what we do is we do all our algebra by manipulating this matrix. Okay, now before I start, okay, I need to say straight out that working with a matrix when you're solving a system of equations with 3 unknowns, okay, is not necessarily faster or simpler than just using regular old elimination like we did before. Okay, but when you move to 4 equations and 4 unknowns, 5 equations and 5 unknowns, it is much, much better, much more efficient to work with a matrix format. Okay, so, let's take a look. I missed. Tony, do we have to choose what pill to take now? Okay, Andrea, are you doing okay there? Can you make your statement? It was a matrix. So what pill top take now? Oh, the pill. You mean to take now. There we go. Okay, I get it. The matrix. Wow, that seems like this. You folks too young for the matrix. Seems so long ago. I guess it remained popular all these years. Folks, there is no choice to make. Math is the only pill you should ever be taking. Okay? All right. So for those of you who've heard of matrices, this is, okay, and this is the very important word. This is an application of this idea of matrices. Okay? In fact, the use of matrices is so, so efficient and so useful that many of you are going to take a course called linear algebra, in which you're going to do all of this algebra and much, much more using matrix representations. Okay? In fact, you're even going to take the idea of a vector and not think of it as a vector anymore. It's going to be a special type of matrix. All right? So this is a very huge topic. We are just scratching the surface, but it is kind of nice to start to get an introduction to it. Okay, but like I said, the reality is solving it via elimination or solving it via matrices is, you know, it's a tough call. I can't say that this is actually faster, but if you want to start working with anything larger than 3 equations and 3 unknowns, then you definitely don't want to get mired in working with elimination. You want to work with matrices. Okay, so now instead of talking about elementary operations, we're going to specifically talk about elementary row operations. So if I multiply both sides of this equation by 2, okay, how am I going to represent that in this matrix form? What would I be doing to this row that would represent multiplying both sides of this equation by 2? Don't think too hard. There you go. You're just going to multiply each term in that row by 2. Okay. Now this is where things are going to be a little different, because when you think back to what we did here is we said, well, let's work with these 2 equations, equations 1 and 2, to create this 3rd equation, or this 4th equation. You know, I called it number 4. Okay. So what you do when you're working in matrix form is you're still adding and subtracting matrices, but then you're going to adding and subtracting rows, but then you're going to replace one of those rows with the new equation. And if you add and subtract another set of rows, you're going to be replacing the row by this new equation. Okay. And the other thing that you're allowed to do, remember that 3rd elementary operation was if I want to switch these 2 rows and put this one first and that one second and this one third, I can put the rows in whatever order I want. So I'm allowed to switch rows as I need. Those are the only operations we're allowed to perform on this matrix. Okay, multiply a row by a constant, add or subtract 2 rows and then replace one of them with the new row, or switch around the order of the rows. Okay, so let's go ahead and do this. And really the best way to do it is just try to do an example. So the way we represent performing these operations, okay, is to draw an arrow, because I'm transforming this matrix into an alternate matrix, which still represents the same system of equations. And what I do is above and below, because sometimes you can do more than one step at a time, is we're going to indicate what the operations are that we're solving. Okay, so when you think about what we did in this equation here, is we said, well, we use this x here to help us eliminate the x term in the 2nd equation. That's how I'm going to consider it, that I multiplied this x term by 2 and then subtracted in order to get a 0 coefficient. But then notice I did the same thing here. I use this x term to help me eliminate the negative 3x in the 3rd equation. And that's what I'm going to try to recreate here in my matrix, is I'm going to use this 1 to help me turn this 2 into a 0 and this negative 3 into a 0. That is my first step. Okay, I'm not going to worry about any of the other numbers. My only focus now is to turn these 2 entries into zeros in the same way that I try to eliminate the x term in both of the other equations. Okay, now this is where, and the book doesn't do this, and I really wish they did, because this is one of those times you do it however you like. It's up to you to trust, you know, to trust my years of experience or not to trust it. But as I've been saying pretty much since day one, and as I think has been shown to be true since day one, is most errors are silly sign errors. And there's something you can do to help you eliminate the silly sign errors. And what I'm going to do is I'm going to avoid ever subtracting rows. I never want to subtract rows. The only thing I ever want to do is add rows together. So instead of multiplying this by 2 and then subtracting the equations, what's my alternative if I want everything to be an addition? What am I going to do instead of multiply this row by 2? There you go. So what I'm going to do is I'm going to multiply row 1 by negative 2. So negative 2 times row 1. Then I'm going to add row 2. And then I'm going to replace row 2 by this new equation. Okay? Because again, I don't want to start having 5, 6, 7 rows to this matrix. I always want to keep 3 rows to the matrix. Okay? So as I start to form these new equations, I'm going to start replacing the rows in the matrix that I started with. Okay? So let's see what that looks like. Okay? So notice here, I'm not changing R1 because I'm adding these two together and I'm replacing row 2. So row 1 is going to stay exactly the same. 1, negative 3, negative 2, negative 9. Okay? And let's do this here. So negative 2 plus 2 is 0. Okay? Negative 2 times negative 3. 6 minus 5 is 1. You see how easy it is by making it into an addition? Is I don't have to think about, oh, I'm subtracting a negative or I'm subtracting a positive number. That I just, whatever the operation or whatever the sign is in front of the number, that becomes my operation. That's why turning this into an addition all the time makes this much easier. Negative 2 times negative 2 is 4, plus 1 is 5, and then 18 plus 3 is 21. Okay? Now, one thing you want to never do, okay, and this is kind of like the golden rule of working with matrices, is you can't change a row and then in the same step use that same row to manipulate another row, okay? But am I changing row 1 here? I'm not changing row 1. So I'm going to save myself some time by also, in the same step, using this 1 to help me eliminate the 3. Okay? So what am I going to multiply to row 1 that's going to help me eliminate row 3? And remember, I want to do an addition. There you go. I'm going to multiply 3 times row 1 plus row 3, and then I'm going to replace row 3 with that new equation, or that new row. Okay, so 3 minus 3, 0. Okay, negative 9 plus 6, 15. And then here, negative 6 plus 2 is, negative 6 plus 2 is negative 4. Okay, and then what's the next one we have? We have 3.
I think you didn't multiply, it's negative 9 plus 6 now.
Oh, there you go. Good catch, folks. Good catch. Okay, sorry, which one was that? That was negative 9 plus 6 is negative 3. Good one. Okay, and then here we've got 3 times 9. Negative 27 plus 8 is negative 19. Okay, now by the way, do these numbers look familiar to you at all? Okay, they look a lot like the coefficients that we had in the previous day's work. Now you notice the signs are a little different because, I did everything with in some cases, I'm not in this one here, but in this first one, because I did additions instead of subtractions. But essentially, I'm doing the exact same work as I did yesterday. I'm just representing everything in this matrix form. Okay? So, what I want to do now is I want to finally determine the value of one of these variables. So, I've done a good job so far. I've eliminated these x's. So now I'm left with these two equations and two unknowns. So what's my next goal here? essentially, that's what I'm going to be working with. I'm still going to write out this whole matrix so we don't create a smaller matrix. But essentially now I want to solve this system of equations. And now I'm going to do an elimination. Okay, except, oh, the only reason somebody's asking why would I do addition instead of subtraction? You certainly can use subtraction, the book does. It just helps to avoid mistakes. And clearly not 100% because I made one myself. It's just because it's a lot easier to make a mistake when you're subtracting numbers than when you're adding numbers. That is the only reason why I'm suggesting we do that. There's no mathematical reason for it. It's more as a way to avoid mistakes. Okay? So now what I want to do is I want to do another elimination. But look what I've managed to do. I have these zeros in the x position. So if I manipulate only equations 2 and 3, or rows 2 and 3, is that going to have any effect on this first row, this first expressions of 0? Not at all. Okay, there really is a brilliance to all this. You know, again, whoever had the initial idea to do this, quite brilliant. So the next thing I'm going to do is I want to eliminate this -3. So I'm going to use this 1 to help me eliminate the -3. So I'm going to do 3 times R2 plus R3, and I'm going to replace R3 by this new row. So 1, -3, -2, -9. I still haven't changed equation 1. Okay, I'm not going to change row 2. Okay, and now, you know, -3 times 0 plus 0. Remember what I promised? These things won't be affected. But now, when I have when I have 3 minus 3, I get 0. Here I've got 15 minus 4 is 11. And here I've got, what is that? That's 63 minus 19, 63, 53, 43, 44. And look what we have. This again should look familiar. Okay? So this is one place where you can now stop. Okay? And what your goal essentially is with your matrix is to get this triangle of zeros in the bottom third. Why is this useful to have this triangle of zeros? What can I now do with this matrix, or at least one particular portion of this matrix that's very useful? And remember, these things represent equations. Do you see a very interesting, useful equation?
In the bottom row,
there you go.
Have them already isolated, and then you can keep moving up and just plugging in the values that you get.
There you go. So this is what we call row echelon form. Okay, and row echelon form essentially means that you've got this triangle of zeros in the bottom left corner. And what that allows you to now do is just solve this. Because remember what this represents: coefficient of x, coefficient of y, coefficient of z, result. So this equation at the bottom just represents 11z equals 44. Z equals 4, which I'm pretty sure is what we got last time. But now that I know that z equals 4, I can now go to row 2 and solve y plus 5 times z, which is 4, is equal to 21. So y is equal to 21 minus 21. And then I can take these two answers and go back to row 1 and solve for x. X minus 3 times 1 minus 2 times 4 is equal to -9. And so x is equal to, so -3 minus 8, -11, so plus 11, and x is equal to 2. Okay? Which I'm pretty sure was the exact same answer we got last time. Yeah, there we go, 214. Okay? So this is certainly one way in which you can solve it using a matrix, but there's actually another option. There's an option to keep going. Because you know the way you were able to look at this right off the bat and say, oh, I can find the value for z very easily. Well, what would I like to see in this row that would help me find y very easily? What do you think I would like to see in that row? There you go. I'd like to see a 0 in this position here. And what would I like to see in this first row? There you go. I'd like to see, essentially, I would like to see another triangle of zeros in the top right corner. So what I would like to end up with is a diagonal of, ideally, 1s, okay? And then just my answers on the side. So let's keep going, okay? So we're not just going to aim now in this case here. We're not just going to do row echelon form. We're going to do what's called row reduced echelon form, or reduced row echelon form. Sorry about that. Okay, so let's keep going. Well, hey, look at this. I've got these zeros in the first two positions of my third row. So any additions or subtractions I do with the third row are not going to affect the first two positions. And that's the very important point to make here, is now we're going to work backwards. Remember how we started, how we used row 1 to start eliminating row 2 and row 3? Now we're going to go backwards. I'm going to use row 3 to help me eliminate terms in rows 2 and rows 1. Okay? The reason being is I don't want to affect all the other nice stuff that I have going on in those rows. And I mean, I could certainly multiply both rows of the equation. I don't have to just multiply one, but what's something really nice we could do with row 3 to make our lives maybe a little easier? There you go. So what I'm going to do is I'm going to do 1 over 11 R3, and then I'm going to use that to replace R3. And so 1, -3, -2, -9, 0, 1, 5, 21. Okay, 0, 0. This now becomes 1, and this becomes 4, which makes sense. Z equals 4. And now, like I said, is I'm going to go backwards. I'm going to use row 3 to help me eliminate this term and that term. Okay, so I'm going to do -5 R3 plus R2 and replace row 2 because I want to get rid of the 5. Then I'm going to do 2R3 plus R1 and replace R1. Okay, to get rid of the -2. So let's see what happens here. 0, 0, 1. So -5 times 0 plus 0, exactly what I wanted. I didn't want to mess up this 0 here. I also didn't want to mess up this 1 here. Okay, -5 times 0 plus 1, still 0. Okay, sorry, still 1 plus 1, so still 1. Okay, now I got to do some work. -5 plus 5 is 0. Good, exactly what I wanted. And here, -20 plus 21 is 1. Hey, what does this row tell you right off the bat? That y is equal to 1. There you go. So let's do row 1, unaffected by this first term, unaffected by this second term. Okay, but now we've got, -2, 2 minus 2 is 0. And here we've got 8 minus 9 is -1. Okay, I'm getting close. The only thing I have left to get rid of is this one here. And guess which row I'm going to use to get rid of that one? I'll talk about that in a second, Ellie. Okay, what row am I going to use to get rid of that? I'm going to use row 2 because, again, look what I have, a 0 on either side. It's not going to affect these two numbers. Okay, so here I'm just going to do 3R2 plus R1, and I'm going to replace R1. So here, what do we have? We have 1. -3 minus 3 is 0. That 0 won't change. Okay, here we have 3 minus 1 is 2. Okay, and everything else stays the same. and I've achieved what I wanted to achieve, the two triangles of 0. Okay, now I can read the answer straight off. X equals 2, Y equals 1, Z equals 4. Okay, this is what we call reduced row echelon form. Okay. Now, this clearly took a long time because we did a lot of talking. Okay, we you know, we're not as quick at doing this type of thing. And like I said, I said right off the back, I'm not going to be guaranteeing that this is faster than what we did before, but it's your introduction into this idea of using matrices. That as soon as you move beyond 3 equations and 3 unknowns, there's no competition. You're going to want to go the matrix route. Okay. So, if on a quiz or exam you want to solve things using elimination, no problem. But again, if you know you're taking linear algebra next year or the year after, I would make the effort to try to get comfortable using this matrix representation. So like I think I just answered that question. Okay, so for this year, I don't think I'm gonna ask any question that forces you to use matrices, but I would say you may as well. You may as well learn something new. Okay, now Ali asked a very good question. What if these questions didn't work out so nicely, that you had all these nice ones that ended up in the right place? So the first thing you can do is, nothing stops you when you're adding and subtracting rows to multiply both rows, to do 2 times row 1 plus 3 times row 2. Okay, the same that you would do when you were solving questions using elimination. Sometimes you have to multiply both equations when you're doing an elimination. And there's something else, and this is the one you're not going to like, is, hey, sometimes you just have to get used to working with fractions. I will tell you, I don't know that I remember much about my first linear algebra course. I can certainly tell you that I remember the horror of working with huge matrices and having to work with tons of fractions, and sometimes you make that one little mistake, and let's just say I'm sure there was some improper words used. Okay, so sometimes they don't work out quite so nicely. In this course here, as an introduction, are you likely going to get mostly questions where it works out relatively nicely? Yes. Okay, because the idea is to get you used to. Okay, so let's take a look. Now, by the way, would I be bothering to do any of this if there were any parallel planes? No. You certainly could, and the algebra would take you to the right place. Okay, but this really is, if you see any equations that are equivalent to each other, or at least planes that are parallel and distinct, then you shouldn't be going to this. So the question is, what happens if there isn't a single solution? Well, let's take a look at what happens here. Okay, now this took way longer than I expected, so let me maybe get to this a little quicker. Okay, any questions we want to ask at this point here? All right, so let's see what happens here. I'm going to create my matrix: 1, -1, -2, 5. Okay, 2, 2, 1, 1, 1, 3, 3, 10. Okay, now the one thing I see here is I'm always very happy when I see a 1 in that top position. If you take a look at the next question, there isn't going to be a 1 at the top position. What do you think I'm going to do in that circumstance? What did we say was one of our, there you go. I'm going to rearrange the rows. because that's one of my elementary operations. Because the whole thing about working with matrices, and this is again much more important when you're getting to much larger matrices, is to keep a consistent algorithm. So even if if there's no way to get a leading one, you're going to divide that row by whatever number it is, and you're going to start with this leading one, because it just makes things a whole lot easier to work with that leading one. So I would say for a 3x3 scenario, 3 equations, 3 unknowns, you can easily stop at row echelon form. Once you started to get to 4, especially 5 and above, you probably want to go all the way to reduced row echelon form. Okay? So again, because this is a very small number of equations, it doesn't really matter which way you go. Okay, when you're working with many more equations, you probably want to go the route of reduced row echelon form. Okay, so here it's following an algorithm, same thing every time. It's going to be negative 2r1 plus r2 replaces r2. Negative r1 plus r3 replaces r3. Okay, I don't even think about it. I just eliminate these two numbers here. Negative 2, 5. Okay. Negative 2 plus 2, 0. This is going to be 2 plus 2, 4. This is going to be 4 plus 1, 5. Okay, this is going to be negative 10 plus 1, negative 9. Okay, please check my algebra as I go, of course. Okay, negative 1 plus 1, 0. This is going to be 1 plus 3, 4. This is going to be 2 plus 3, 5. This is going to be negative 5 plus 10, 5. Now, I'm just going to keep going. I'm hoping you're already seeing where this is going. Next step is to eliminate this value here. So I'm going to do negative R2 plus R3 and replace R3. And let's see what that gives us. Row 1 doesn't change. 1, negative 2, 5. Okay, 0, 4, 5, negative 9. Okay, negative 0 plus 0, still 0. Negative 4 plus 4, 0. Negative 5 plus 5, 0. 9 plus 5, 14. And what's the issue? What does this represent, the 0, 0, 0, 14? What is that telling us? It is telling us row 3 is claiming that 0 is equal to 14, which is a contradiction. And so what's our conclusion? Given that we assumed there was a solution and we came out to a contradiction, what is the conclusion based on that? There you go. I agree. It does seem even more, kind of puts a more oomph to it when you say it in French. Okay, no solutions. Now, if I were to ask you to give a geometric description of what's going on, well, you know, oh, I've got 3 planes, none of them are parallel, there's no solution, hence, what can I say geometrically here? What scenario would this represent if I have no part the triangular prism? Now, here, all they asked us to do was to solve the system of equations. So here, that's all I have to say, is that there's no solution. But if they're asking me for the geometric interpretation, okay? So this was, I forgot whose question this was, is what happens when there's no solution? Well, it's the same answer as always. The algebra will take you there, okay? The algebra will do its job, okay? So I think I might only get to do one more, so I might just add the last one as, I think I might even have a video on this. I'm hoping I do, so I can just post it, okay? Or if you want to stick around for a couple of minutes, we can do it together, okay? But what did we say? What's the first thing I want to do here? It's the first thing I want to do with that row. There you go. I would prefer, if at all possible, not to have that leading 2. I'd like to have a leading 1. So I'm just going to move everything up. I'll put 1, -1, -1, -4. I'll put this one on the top row. Doesn't matter which one comes next. -7, -4, -37. And then here we have 2, 0, -1, 3. Okay. And so now I just go along. So try to do this and stay a step ahead of me if you can. Okay. So negative R1 plus R2 goes into R2. -2 R1 plus R3 goes into R3. Okay, so 1, -1, -1, -4. Here, -1 plus 1 is 0. That's a 1 minus 7 is -6. Okay. Here we've got 1 minus 4 is -3. And then here we have 4 minus 37 is -33. Here we've got -2 plus 2 is 0. Here we've got 2 plus 0 is 2. Here we've got 2 minus 1 is 1. And then here we've got 8 plus 3 is 11. Okay. Now, I notice I'd like to get rid of this 2 here, so it'd be really nice to, simplify this if we can. Okay, so I see I can divide by -3. So I'll do -1/3 R2 into R2. Okay, so here 1, -1, -1, -4. That's 0. That's going to be 2, 1, 11. 0, 2, 1, 11. Oh, this is looking very interesting because now when I do -R2 plus R3, which is going to replace R3, -2 plus 2, 0. -1 plus 1, 0. -11 plus 11, 0. And so how are we going to interpret this row of zeros? Well, that tells me that 0 equals 0, which of course is always true. So what's our interpretation of this? The interpretation is that we've got infinitely many solutions. Okay? But of course, I would like to do more than just say there's infinitely many solutions. Ideally, I would like to describe them. Okay? Unless it tells me otherwise. And sometimes you're only interested in the scenarios where there's one and only one solution. Okay? In this case here, let me try to describe those things. So this row now becomes kind of ineffective or not very useful at this point. So let's focus on what the top 2 rows tell us. So thinking about what we would have done in the past, how might you use row 2 to help start this trek to describing these solutions? What could I use row 2 to help me do? There you go. I can use it to help me isolate a variable because I know that this represents 2y plus z equals 11. And so I'm able to write z in terms of y. And then I'm doing exactly what I did before. Now I can use this to go into the first equation, x minus y minus z. But wherever I see a z, I'm now going to replace that by -2y plus 11 equal -4. And I can now write x in terms of y. Because what do we have? -1 plus 2 is 1. Take that to the other side, -1. And then here we have -11. Take that to the other side. -4 plus 11 is, I guess, 7. And now I can give my solutions. Okay. Let y be my t value, my parameter. And so here we have x is negative t plus 7, y is t, and z is negative 2t plus 11. Okay. And so yet again, the algebra takes me where I need to go. Because remember, in the end, what this represents, it just represents doing the exact same thing as we did before, just in a different format. That's all we've really changed is the format, okay? The other thing that has changed is the pattern that we follow, the algorithm that we follow. When we were solving things using elimination, we kind of didn't worry about whether we were eliminating y's or eliminating z's or x's, okay? The difference that does come in is I do follow this algorithm of always eliminating the x's and then always eliminating the y in that third equation, okay? So that is something that does change. In a three equation, three unknown context, is that necessarily always the most efficient way of doing it? Not necessarily. But this is kind of like our introduction to this idea of using matrix representations to solve these types of equations. And again, the matrices just get used. This way of representing data is extremely useful. Okay. Now this one here, again, is it's a fairly straightforward one. This one does come out to be a single solution. So I'm happy to do it if people want to stick around to see one more example, or if everybody's fine to do it unknown. But I'm happy to just do it if people want to do it. And if you want to leave, you can leave because I don't want to keep you past 3:30. Okay. Yeah, the last quiz will be dedicated to matrices. Okay, so not the one next week. The one next week only goes up until solving systems by elimination, and then the week after will be matrices. Okay, do I have people who want to stick around for one more? Okay, I see a few, so we'll do it. Like I said, if you need to leave, please don't hesitate. I won't take it personally this time. All right. And, oh, sorry, I misplaced my pencil. There we go, we got it. Okay. Okay. And what I want to try to do here is I want to try to do this quickly. I want to try to, like, I'm going to sort of talk it out. You'll hear me talking it out. But in order for this to be useful, you have to become quick at it. Practice is the way you're going to do that. Okay. So 1, -2, 3, 1. Okay. 2, -3, 4, -2. And then 1, 0, 1, 7. Okay. So always doing the same thing. Negative R1 plus R2 gives me R2. Negative, of course, that was supposed to be -2. And then negative R1 plus R3 goes into R3. Okay, 1, -2, 3, 1. Okay, -2 plus 2, 0. Okay, 4 minus 3, 1. -6 plus 4, -2, and then -2 minus 2, -4. Okay, so here, -1 plus 1 is 0, 2 plus 0 is 2, -3 plus 1 is -2, and then -2 plus 7 is 5. Okay, -2R2 plus R3 into R3. 1, -2, 3, 1, 0, 1, -2, -4, 0. So -2 plus 2, 0. 4 minus 2 is 2. And then 8 plus 5 is I feel like I made a mistake here because I don't think this is what the answer should be. So let's take a quick look at at my answers here. Okay. -2 plus 2 is 0. This is 4 minus 2. Row 3, 5 should be 6. So let's take a look. This one here, what did we have? We had -1 plus 7 is 6. Good catch. Thank you. Who was that? Andrea. Good catch on that. I was pretty sure I picked nice numbers for this one here. Okay, so this ends up being 8 plus 6 is 14. Okay, and so from here, I could solve 2z equals 14 and solve that way. But just for the fun of it, let's keep going to do reduced row echelon form. So first thing I'm going to do is I'm going to do 1/2 R3 into R3 just to make this nicer to work with. 1, -2, 3, 1, 0, 1, -2, -4, 0, 0, 1, 7. Okay, so right off the bat, I know that z equal to 7 is one of my answers. Okay, so let's eliminate these two. So what do we have? We have -3R3 plus R1 replaces R1, and then 2R3 plus R2 replaces R2. So I can eliminate those two. Okay, so what do we have? We have 1, -2. Okay, -3 plus 3 is 0. Here we have -21 plus 1 is -20. Okay, 0, 1. Here we've got 2 minus 2 is 0. And here we've got 14 minus 4 is 10. And 0, 0, 1, 7. So there we go. Y is 10. There's another one of our answers. And let's do the last step. 2R2 plus R1 replaces R1. Okay. Well, maybe you made a second mistake to cancel out the first one. Okay. So here, where are we at there? This should just be 2. 2 minus 2 is 0. That's just 0. And then here we have 20 minus 20 is 0. And so here 0, 1, 0, 10. 0, 0, 1, 7. So we have x equals 0, y equals 10, z equals 7. Okay. So fair bit of writing. Okay, like I said, you will undoubtedly, if you take a linear algebra course, you'll have some nightmares doing 4x4, 5x5 of these matrices, and you're going to have to be exceptionally careful and second guessing yourself throughout. Okay, but in the end, this is a very compact way to deal with multiple equations and multiple unknowns, especially when you go beyond 3. Okay, are there any questions we want to ask here?